Hello everyone, welcome back to another video. Today we're going to be going over the algebra content area for the SAT and PSAT math section. This is the first major content area that you should know for the exam, and some of the concepts that we're talking about here are going to be built upon in later content areas, so please make sure you're understanding this section really well. So we're going to start from the beginning. We're going to start with linear equations and inequalities. So what exactly is a linear equation? Let's start with that. A linear equation is basically any equation with variables, operation signs, and integers, or constants, for example. So like x plus 5 equals 10. That's an example of a linear equation. And one of the most important foundational skills that you need to know is how exactly do we solve linear equations. And when we talk about solving linear equations, we're talking about solving for the variable. So in this case, using this equation, right, let's say we want to solve for x. So in this case, right, we want to have the variables. To solve these types of equations, we want to have the variables on one side of the equation. So we want to have x on this side, and then we want all the constants on the right side of the equation. So how do we get x by itself? We're going to subtract both sides by 5. So that way we're isolating it by itself. So when we do that, we get x equals 5, which is the answer here. Okay? We're going to do a two-step equation now. So that's a one-step equation. But a two-step equation, there's two steps to solve the linear equation. So if we had 2x minus 5 equals 13, for example, and we want to solve for x. So again, the first thing we want to do is we want to have the variables on one side of the equation and the constants on the other side. So we're going to add 5 to both sides, and we're going to get 2x equals 18. And then our second step is going to be to finally solve for x. So what's attached to this x? 2 times x. So we want to divide both sides by 2, so that way we can get x by itself, which would be x equals 9. So remember, you're doing the opposite of the operation that is shown to kind of cancel it out and solve for x. So if you're seeing subtraction, you want to add. If you see multiplication, you want to divide, and vice versa to solve for your variable. Now, linear inequalities is basically the same thing. We'll first go over inequality signs. So this sign means greater than. So the quantity that's on the left side of this inequality is greater than the right side. This is less than. So the quantity on the left side is less than the one on the right side. This one is greater than or equal to. The line underneath means equal to. So the quantity on the left here is greater than or equal to the quantity on the right. And then we have less than or equal to, where we have the quantity on the left being less than or equal to the quantity on the right. And then you won't see this often for inequalities, but if you see an equal sign with a line through it like this, that means not equal to. But it's mainly you're going to have to just worry about these 4 signs up here. So we solve for linear inequalities pretty much the same way as we do equations, with one major difference though that I'm going to highlight in this first example. Let's say we have negative 9x is greater than 54. Whenever you multiply or divide by a negative number, you need to make sure you flip the inequality sign. So in this case, we have a greater than sign right here. We're going to divide both sides by negative 9. And when we do that, we're going to get x. We're going to flip this greater than sign to a less than sign. So it's going to become less than negative 6. If it was a greater than or equal to, it's going to become less than or equal to, and vice versa. So that's an important thing to remember. If you're multiplying or dividing by a negative number, you're flipping the inequality sign. Outside of that, it's pretty much the same process as solving for a linear equation. So now we're going to move on to word problems for linear equations and linear relationships. Specifically, it's mostly the same idea of what we've been doing, except it's now in a word problem. So like, for example, let's say, I'm going to give an example like what the SAT could ask. Let's say we have a car that's worth $17,000 when you buy it initially, and its value decreases by $2,000 every single year. How many years is it going to take for that car's value to become $9,000? So here we have an equation, a linear relationship in the form y equals mx plus b, which this is mainly your linear equation right here. that you need to worry about. That's the main linear equation, and you typically see it more with graphing, which we're going to get to later, but that's just the idea for linear equations in general. So we want to take this information that we were given and we want to write it into a linear equation so that way we're able to understand it better than just a bunch of words. So 17,000, that's your initial value. This is your B, right? This is what the car was worth when you bought it. All right, it's decreasing at a rate of $2,000 per year. Decreasing. This is going to be your slope. And in this case, it's going to be negative since it's decreasing every year by $2,000. And 9,000, we want to figure out how many years, right? Years in this case would be our X. We want to figure out how many years it takes to get down to 9,000, which would be our Y in this case, okay? So if we plug our values into this linear equation, we have 9,000 equals negative 2,000x plus 17,000. Let me write the 7 a little better. Okay, 17,000. So now we just need to do what we've been doing for solving linear equations. We're going to subtract both sides by 17,000 to get x by itself. And when we do that, we're going to get negative 8,000 equals negative 2,000x. And finally, to get x by itself, we are going to divide by 2,000. Okay. I guess my whiteboard is stopping here. Okay, so 2,000, sorry for the crunched up space. And if we were to do that, that's going to get us x equals 4. Remember, these are negative signs as well. So the negatives are going to cancel out. So 4 years is how long it's going to take for this car to depreciate to $9,000. So when you're doing linear relationships, right, what is a linear relationship? It's basically where you have like a y equals mx plus b relationship, where as x increases, y is increasing by a certain amount. That's your slope. That's your m. So when you're looking at linear equation problems, try to figure out what is your initial value, what is your b, what is your slope, and then what is your x and y. You're going to be given 3 of these variables, and you're going to have to find the 4th one, which you can do using simply solving a linear equation. So that's the idea behind word problems for linear equations and linear relationships. So on to the next topic of graphs. So now we're going to talk about graphs of linear equations and functions. Those are basically interchangeable. But when you're doing a graph, there's typically many ways that we're going to analyze a graph. So let's first talk about creating a graph of a linear equation. You can be either given an equation itself and asked to plot it or graph it. Well, you're not going to be like directly graphing, but you could have to like pick a graph from one of the answer choices. Or you could be given a table, and then you're going to have to do a graph that way. So let's try a table example, actually, because why not? We have x and f of x. We have 0, 1, 1, 3, 2, 5, 3, 7. So we're going to graph this function first, and then we're going to try to find the actual linear equation for it. So let's graph. Let's pull out my graph here. That is a terrible line. Let's draw a little better of a line. Okay. All right, so we have our graph here. We're going to go like 1, 2, 3, 4, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. All right. So we're going to label our axes. That's very important to do that. And then when we're talking about graphing functions, right? Well, in this case, we're given points. So let's just graph the points in the order that we have it. So 0, 1, that's going to be right here. All right. 1, 3, that's going to be right here. 2, 5 is going to be right here. And then 3, 7 is going to be right here. And we can go ahead and connect these with the line to the best of my ability. That's not a great line, actually. Okay, we're going to pretend this is a good line. It's obviously not perfect, but that's okay. So we want to try to write this in y equals mx plus b form. So what I would do is I would do this. Let's first figure out our y-intercept. That will give us our b. So they give us this value, 0, 1. That is your y-intercept. That's where it's touching the y-axis. So My b is going to be plus 1. Okay, so then how now can I find my slope? I want to use a different point now. Or we can actually do this actually. Let's find the slope between 2 points, and since it's a linear equation, it's going to be the same slope throughout. It's good, so we can actually highlight this too. So how do we find slope? Slope formula is y2 minus y1 over x2 minus x1. So if we call this like our x1, we call this our x2, we call this our y1, and we call this our y2, right? Because it's really the points 1, 3, and 2, 5. Our slope formula would be y2 minus y1, 5 minus 3, over x2 minus x1, 2 minus 1. I have no idea why my whiteboard is stopping down here. That's really annoying. 2 minus 1. So that leaves us with 2 over 1, or 2, as our slope. Okay, I apologize again for the crowding here at the bottom, but I did not realize my whiteboard was going to end like right here. That's really annoying. But our slope in this case is going to be 2. So our slope here is 2, and we have x and then y. So this equation is reflected by this table and then by this graph. So if we want to like continue the line in this direction, if we're going up 2 to the right one, like 2 over 1, because remember slope is rise over run, y over x. So if our slope is positive 2, that means if we go up 2, we have to go to the right 1. And if we're going down 2, we have to go to the left 1. Okay? So down 2 to the left 1, 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 like this. All right? So this would be your line, pretty much. Okay? So that's how you graph it from a table. Sometimes you'll be given a graph, and you'll have to figure out the actual linear relationship, like the linear equation. If that's the case, if you have the y-intercept, use that as your b. If you do not, try to find the slope between 2 points to figure out your m first, and then after that, you can plug in one of the points with your slope and just do a simple equation, linear equation, to figure out b. That'd be like your missing variable in this case, okay? So that's going to be all for those kind of problems. For in terms of graphs, you'll either have to like pick a graph from an equation or from a table, or identify like an equation from a graph, which again, all ties back into knowing slope and linear equations, knowing how to solve for those. All right, let us go ahead and move on to the next topic of systems of linear equations. So when we talk about systems of linear equations, we're talking about two equations with 2 variables in them. What does that mean? We can have something like x plus y equals 5 and 2x plus y equals 10, something like that. So we have 2 equations that have 2 variables in them, and let's say we want to solve for the solution in this case. So there are 3 main ways we can solve equations: either substitution, elimination, or graphing. So I'm going to do elimination for this problem because it's the simplest. How do we know which one to do for each type? So graphing is kind of rare. You really only want to do graphing if you can easily get both the equations into y equals mx plus b form, which, I mean, in this case, technically yes, because all you'd have to do is just move over the x to the other side, and you can do that. But this is why I want to use elimination. You want to use elimination if between like the x's and between the y's, there's like your least common multiple is like really small. For like, so let me illustrate an example. For here, right, we're looking at the x terms alone to start with, right? We see we have a coefficient of 1 here and 2. So what's the least common multiple between 1 and 2? Well, it's 2, right? But between the y terms, these are both 1s. And what is the least common multiple between 1 and 1? It'd be 1. So for elimination, we want to basically eliminate a variable. So that way we just need to solve for one variable, and then we can take the value that we get for that one variable and plug it into one of the equations to figure out the other variable. So it's really easy to eliminate the y variables because we're going to be adding these equations together. And what that means is if we're adding these equations together and we want to eliminate the y variable, then one of the y variables need to become negative, right? So that way plus y minus y, right? Y minus y equals 0. It cancels out. So basically, for one of these equations, I'm going to pick the top one. We're going to multiply it by -1. So that way we get that negative y, and when we add it to the second equation, we can cancel out the y's. So I'm going to rewrite this first equation down here as negative x minus y equals -5. And then I'm going to have a plus sign on the outside, and I'm going to do 2x plus y equals 10. I'm keeping the second equation the same because we don't need to change it. Sometimes you might have to. You might have a case where you do need to change both variables so that way you can get to that lowest LCM, lowest least common multiple, and eliminate variables. That also might be necessary. But in this case, we're just going to add these two up. We're going to cancel out these, right? Y minus y is 0. And then we're going to add negative x plus 2x. Negative 1 plus 2 is just x by itself. And then -5 plus 10 is going to give us 5. So now we can plug this back into this original equation here. And we have, we substitute 5 in for x. So 5 plus y equals 5. So y is going to be 0. Simple one-step linear equation. So our answer is going to be x equals 5, y equals 0. Or you can write it as an ordered pair of 5, 0. Okay? Let me try to think of an example where you have to manipulate both equations for an elimination. So that way we can kind of get a good problem. So let's try 2x plus y equals 10. And then we're going to have 3x plus... Actually, no, I don't want to do y. 2x plus 3y. Let's do that. Equals 10. And then we're going to have 3x plus 5y equals, I don't know, let's say 15. I'm warning you, this is probably going to have fractions for answers. This is me trying to make up one on the run. But in this case, we see that we are going to have to manipulate both equations, right? Because what is our least common multiple between 2 and 3, right? It's going to be 6. Remember, 2 times 3, 6. Their greatest common factor between them is 1. So 6 divided by 1 is going to give you 6. That's a trick for least common multiple, by the way. Just multiply the two numbers together and divide by their greatest common factor. But so in this case, it's going to be 6. That's our least common multiple for our x terms. How about our y terms? Well, 3 times 5 is 15. Greatest common factor is 1, so 15. So 15 versus 6. I probably want to do the one with 6. It's going to be a little easier. So what we want to do is we want one of the equations to have a negative 6x, and we want the other equation to have a positive 6x, right? So that way we can eliminate that variable. So I'm going to go ahead and, it doesn't really matter which one you multiply. Negative-wise, you have to multiply this by 3 and 2, though. I'll pick the bottom one to multiply times -2, though, right? That makes sense because we're trying to get to 6x and -6x, respectively. So if we rewrite this top equation, we're going to have 6x plus 9y equals 30. And then our bottom equation is going to be -6x minus 10y equals -30. So, oh wow, actually I unintentionally didn't realize. Okay, so we're not going to be having variables here, guys. Alright, so we're going to basically add these, right, together. So when we add it, we're going to cancel these x terms out. 9 minus 10, that's -y, equals 30 minus 30, which is 0. So our y is equal to 0, because remember, 0 divided by anything is still 0. So now we can plug this back into, let's say, the top equation, right? We substitute 0 for y. So 2x plus 3 times 0 equals 10. 3 times 0 is just 0, so 2x plus 0 equals 10. That basically goes away, so 2x equals 10. And then divide both sides by 2 to get x equals 5. So 5, 0 is our answer for this solution, for this set of equations. Not intentional at all to get the same solution. I just was trying to illustrate to you guys that sometimes you might need to multiply both equations by a certain number to eliminate easily. All right. Let's quickly do a substitution problem, and hopefully we do one where the solution is not the same as these last two problems. So we have x plus y equals 6, and then 3x plus 2y equals 15. Okay, I know for a fact this isn't going to be the same solution. So in this case, yeah, you can do elimination here, but let's try substitution. What does substitution mean? We're solving for one variable. We're solving for one variable in terms of the other variable, and then we're going to take that expression and substitute it in the second equation for the variable we solved for. So in this case, it doesn't really matter which variable you solve for because it's the same one step. You're either going to get x equals 6 minus y or y equals 6 minus x. I'll solve for y. So we're going to move x to the other side. 6 minus x or negative x plus 6, doesn't matter. So now we're going to take this expression and we're going to substitute it in for y in this equation. So 3x plus 2 times 6 minus x equals 15. So now we're going to distribute this 2 here. We're going to have 3x plus 12 minus 2x equals 15, right? We're going to combine like terms, this 3x and this minus 2x, to get x plus 12 equals 15. Now one-step equation, we want to get the variable by itself, subtract both sides by 12, and we will get x equals 3 as our x term. So now that we have x equals 3, we're going to rewrite this a little bit better, but we're going to have to plug this in. We're going to plug this into the solved out equation that we have here, so that way it's easier to figure out y. So y is equal to 6 minus 3, so y is going to be 3. So 3 comma 3, that's our solution to this set of equations, okay? That's how you do substitution. Again, if you really wanted to, you could have done elimination. The nice thing about the SAT and PSAT math section is you don't need to you need to show your work for you to get the right answer, but it's not like your work is going to get checked. So as long as you're getting the right answer, it really doesn't matter which method you use. And then we'll really quickly try to do a graphing one. So we're going to do, let's say x plus, no, I'm tired of doing x plus y. Let's do x minus y. Let's spice things up. X minus y equals 2. And then we're going to do 2x plus y. Okay, let me think this one. 2x. We'll do 2x minus y, actually. 2x minus y equals 5. Okay. We're going to be graphing here. Again, you can very easily do elimination and get the right answer, but we're going to do graphing for this question. So for graphing, we want to get into y equals mx plus b form, aka we want to get y by itself. So for this top equation, we're going to first subtract x from both sides to get minus y is minus x plus 2. And then we're going to divide by negative 1 to get y equals x minus 2. And then for this equation, we're going to once again move 2x over to the other side and then divide by negative 1 to get 2x minus 5. So these are the two equations that we are going to be graphing. So let's go ahead and draw our graph. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. All right, we're going to label our x and y axes. All right. And then we're going to pick one of these equations and just graph it. So let's start with x minus 2. When we graph, we're going to start with this y-intercept. So 0, negative 2. That's going to be right here. And then follow the slope, right? The slope is 1. That's 1. So up 1, right 1, or down 1, left 1. Both work. So up 1, right 1. That's going to be here. Up 1, right 1. That's here. Up 1, right 1. Up 1, right 1. And then down 1, left 1, down 1, left 1, down 1, left 1. So this is our equation, the best line that I can draw. All right. Wow, it doesn't even go through this point. Okay, cool. So we're going to pretend this is a straight line. All right, awesome. So this is basically our linear equation. And then now we're going to do our second equation, 2x minus 5. So again, we're going to start with our y-intercept. 0, negative 5, that is going to be right here. And then we're going to go up 2 to the right 1, up 2 to the right 1, hold on, up 2 to the right 1, right here. Okay, up 2 to the right 1, up 2 to the right 1. All right, so like this, basically. All right, that's our equation here. So now to figure out the solution, we're just seeing where do the lines intersect. They intersect right here at this point, right? So what is this point? This point is 3, 1. So that is the answer for this set of equations. And if you were to plug these values back into your original equations, right, 3 minus 1, that's 2. 2 times 3 is 6 minus 1, that's 5. So it works out. The solution is correct. So again, try not to do graphing as much unless you're either you need to because you're given like graphs in your answer choices, or if you can easily get it to y equals mx plus b form. All right, now let's go ahead and move on to the next topic of systems of linear equations, word problems. So for word problems, what we're going to do is we're not actually going to solve one. We're just going to set them up because I think you guys already know how we can solve them. So when it comes to setting up systems of linear equations from a problem, right, it's just all about can you interpret the most important information from the word problem. That's a recurring theme within the SAT, right? Can you interpret word problems to get the most important information, to take what they give you in words and convert it to algebra? So if, for example, we're at an amusement park, right, and we have adult tickets that are $10 and then child tickets that are $5. And let's say that on a particular day, we have 120 adults and kids that come to the amusement park. And the total money that the store makes, the amusement park makes is, I'm making up values, guys, because we're not solving it, $4,000, for example. How many adults and how many kids came that day to the amusement park? So I'm doing this example just to kind of illustrate to you guys how are we going to take the information we have, this information, and turn it into a systems of equations that we can solve using one of the methods we just talked about. So let's focus on this information. We're going to focus on this first, right? There's 120 adults and kids that came. In other words, the total number of adults, if we say like adults is X and kids is Y, the total number of adults plus kids equals 120. I don't want to put this here because it looks like a minus. I'm going to put a star here or something. All right, so X plus Y equals 120. That's our first equation. The total number of adults and kids that came is 120. So boom, we've taken this information and we've made it into a equation down here. Now, the other equation that you're going to use involves the ticket price, right? If they made $4,000, we said adult tickets are $10 and child tickets are $5. So the revenue you're going to get from adult tickets is 10x, right? If you sell 10 adult tickets, you're going to get $100 because each ticket is $10. And the revenue you make from child tickets is going to be 5 times the number of kids, right? If we sell 5 kid tickets, we're going to get $25. 5 times 5 is 25. And since the total we made from both is 4,000, that's what this equation is going to be set equal to. So that would take care of this remaining information here. And that highlights all the major boxes for our systems of equations. Now we can solve for X and Y using the equations that the methods that we talked about earlier, and you'll be able to get your answer for this question. We're not going to solve it again because I just wanted to illustrate to you guys how you can take information from a word problem and then convert it into equations. That's probably the most important skill that will help you a lot because I'm confident you all can solve equations once you get down to this stage. It's just a question of can you take information, the most important information from the word problem, and be able to convert it into algebra. That's the biggest skill. All right? So make sure you're doing that. You're highlighting the most important information from the problem and you're able to convert it into 2 equations for systems of equations. All right. Next topic of linear inequality word problems. So linear inequality word problems are basically similar to linear equation word problems where you're taking information they give you in the problem and you're trying to convert it into algebra that you know. So let's say, for example, you have $48 and you're at a arcade, and each game at the arcade costs $1.50, right? How many what is the maximum number of arcade games that you can pay for using the money that you have? So let's break down what we have here. We have $48. $48. That's the total amount of money that you have. And we have $1.50 per game. So our game is like our X here, right? So if it's $1.50 per game, that means it's going to be 1.5 times X, right? If you play two games, you're paying $3, 1.5 times 2. And then our maximum amount of money that we have is 48, right? And here's the key word. This is where it's an inequality and not an equation. Maximum. What is the maximum number of games that you can play? In other words, you cannot have a like a decimal or a fraction number of games because it's maximum. You can only play a whole game. So this is where your inequality symbols come into play. We have a maximum of $48. We cannot go over the $48, right? So that means that our inequality sign is going to be towards the 48 because we can't go over 48, right? We can go up to 48, so we can actually do a less than or equal to sign. We can go up to 48, but we can't go over 48. So less than or equal to works out for this equation because we can't have a value greater than 48. So then obviously you would just divide both sides by 1.5 and you'd get your answer. But that was how you would take information from the word problem and convert it into an inequality. All right? And then the last topic we have in algebra is going to be graphs of linear systems and inequalities, which we kind of already touched upon when I went over solving linear equations by graphing. But we'll do an inequality one since it's a little bit different than a equation one. So let's say we have x plus y is greater than 5. And then 2x plus 3y is greater than or equal to 12. Let's try that, okay? Yeah, we'll start with this to start with. So we want to plot these inequalities in a graph, right? We're going to do each inequality, we're going to graph by itself first. So here's what we're going to do. We're going to first label it out. Well, actually, before we do that, let's solve for y. That's probably the best thing to do. Let's solve for y so we get it into mx plus b form. So we're going to move x over to the other side, negative x plus 5 to get this into y equals mx plus b form. Here, we are going to first move 2x over to the other side, so negative 2x plus 12. And then we're going to divide by 3 to get negative 2/3 x plus 4. All right, so that's what we're dealing with for our two equations. So we're going to first graph this first equation. I don't know why I keep calling it an equation. My bad, guys. Inequality. We're going to be graphing this first inequality on the graph first. All right. So, and then I'm going to go up by 2s actually to save space on the y-axis. So 1, 2, 3, 4, 5, negative 1, negative 2, negative 3, negative 4, negative 5, 2, 4, 6, 8, 10, 12, negative 2, negative 4, negative 6, negative 8, negative 10, negative 12. All right, so first equation, first find the y-intercept. It's going to be in between 4 and 6, so right here. Negative x, so down 1 to the right, down 1 to the right 1, so it'd be actually here. Down 1 to the right 1, down 1 to the right 1, down 1 to the right 1, down 1 to the right 1. So basically like this. Actually, okay, before we put the line in, since we have a greater than or less than sign, there's no equal to underneath, your line is actually going to be dashed. If there was a greater than or equal to sign or a less than or equal to like here, then it's a solid line. So it actually would be a dashed line. We're going to do it to the best of our ability here. All right, so like this would be our line. All right, it's not 100% perfect, but that's the idea. All right, and when we're solving systems of inequalities, we're going to be shading a particular area of the graph that satisfies both inequalities. So we're going to pick a test point here on one of the sides of the line. It shouldn't be on the line, but one of the sides of the line. So either a point up here or like a point down here. And we're going to see if the inequality is satisfied. If it is, then that's the area that we're going to be looking at when we plot our second line as to where the two might intersect. If it's not, then it's going to be in the other side. And again, when we plot our second line, that's what we're going to be looking for. So the easiest test point to use is just 0, 0. So if we use that for this top inequality here, we have 0 is greater than negative 0 plus 5, or 0 is greater than 5. Is this a true statement? No, it is not. 0 is not greater than 5. So I know that anything including 0, 0, so all this area down here cannot be where the solution is. It has to be up here. So that's where we're going to be looking for solutions after we plot our second line. So now we're going to plot our second line. And we're going to connect it with a solid line this time because it's a less than or equal to sign. So we're going to start with our y-intercept of 4. Up 2 to the left 3. Up 2 to the left 3. Down 2 to the right 3. Down 2 to the right 3. All right. So something like this. Apologize, my lines aren't the best, guys, but that is what we are dealing with here. All right. So we want to pick a point that would be, oh, I did it again. All right. Sorry, guys. We're going to make this a greater than sign. Actually, my bad. Because it's not going to work out if we do this. Okay. So we're actually going to make this a greater than sign. Apologize again, guys. All right. So we figured out that we want to pick a point up here as our point that we're using, because that's where we identified this is the area that we said that would satisfy the first inequality. So we're going to pick a point here, let's say 2, 8, and we're going to plug it into this inequality and see if it works out. So 8 is greater than or equal to negative 2/3 times 2 plus 4. So 8 is greater than negative 4/3 plus 4. So remember, when we add fractions, we want to convert this to a common denominator. So like multiply the top and bottom by 3 to get negative 4/3 plus 12 over 3. So 8 is greater than or equal to 8/3. That would be correct. That does work. On the actual SAT, PSAT math section, like it will work out. You're not going to be like changing stuff mid problem like I am, but I'm coming it up off the top of my head. So I want to make sure I give you guys good examples. So this works. So that means this area here, that would be what we're shading for the answer, okay? Because this is the area that is being satisfied by both inequalities, right? Because we said after this first inequality, it's going to be up here. The second inequality, it agreed it was also up here. So hence that would work. That would be the answer. So this is the area that you would be shading for your answer. All right. So that's going to be it for this algebra video. Sorry again to change up that last problem at the last second, but I wanted to make sure that it was correct. I was giving you guys a good example. So apologies about that. But that is the algebra section. Again, please make sure that you know every single topic in this section, because this is a very important section. And yeah, please make sure to like and subscribe. Let me know if you have any questions. Thank you all for watching, and I will see you all in the next video. Take care, guys.